So, well, maybe we don't need a lot of presentation, but we'll just continue with the course as we left it yesterday. Okay, thank you. I will start by mentioning some missings yesterday. So some missing. First thing that in the first result I gave, I think that I didn't give the converse. The first result is the following: that a topological space is Hausdorff if only if every net has at most one limit. I think that I only give the proof of one application. So this application, I assume that limits are unique. And we want to show that the space is Hausdorff. So let X and Y, two different elements in X, and assume that for every we will argue by contradiction as usual. We will assume that for every neighborhoods of V of X and W of Y, the intersection is not empty. So there exists an element that I called XVW belongs to this intersection. And this defines a net. So we will get on contradiction by showing, we will show that the net XVW indexed by VW in NX cross NY converges to X and Y. So, and this gives a contradiction. So it is sufficient to show that. So let's take U, any neighborhood of X, and we need to show that the net is eventually in this neighborhood. So if I take, I can call this alpha. So for alpha 0 equal to U and W, W is anyone, we have the following: if VW is more or equal than alpha 0, and this means that U is contained, V is contained in U. This implies that X alpha equal X VW is contained in V and in W, and this is contained in U. So we show that for this alpha 0, for every alpha more or equal than alpha 0, we have this. So X alpha converges to X. In a similar way, we can show that X alpha converges to Y. So this is the application that I forgot to prove yesterday. Okay. Another thing that was missed yesterday is the statement, the last statement concerning the universal net. The right statement is the following. In a topological space, a net x alpha, let X be a topological space. Then X is compact if only if every universal net converges. So if the space is compact, so this allows to give a very short proof of the Tikhonov theorem. But yesterday, the statement is not clear. I write every subnet. So, for example, for this application, if every universal net converges, then if we take a net, we know that this net has a universal subnet, and it's okay. I forgot also to give an example. I promised to give an example of a compact space for which every sequence has no conversion subsequent. So, to give this example, I take H, the collection of confined subset of N, and X is equal to -1 power H, all function from H to -1, 1. I will define Fn in X by Fn of A equal 1 if N belongs to A and -1 otherwise. I will show that this net, of course, by Tikhonov theorem, this is a compact space, and I will show that this sequence has no conversion subsequence. So if we take any subsequence, f phi of n, and to show that we mentioned yesterday that in a product topological space, a net or a sequence converges if only if every component converges. So this is called the topology of pointwise convergence also. So to show that this diverges, it is sufficient to find a subset A such that f by n of A diverges. That we will take A equal to phi of 2n, and n is in n. Now, if we compute Fn of A, so Fn of A is equal to 1. So if n is even, so it's 1, and so it just then check that it's -1 power n. So does not converge. Okay.
It's phi n.
Phi n, yeah. Okay. So if you use Tikhonov theorem and knowledge about convergence in product space. So the example is not okay. Also, last thing that I missed to mention that we can make a remark. If we work in a product space, we already said that the lattice alpha converges if only if x alpha of I converge in xi for every I. And we can make this is false for cluster point. This means that if x alpha of I has, I will say that if xi is a cluster point of x alpha of I for every I, this does not mean that x equal xi is cluster point of x alpha. Simply we can take a sequence in R2, and take this sequence 1 0 0 1, etc. So 1 is a cluster point for the first component, and 1 is a cluster point for the second. But so a very close idea is used when we prove Tikhonov theorem, but it can make confusion. Before giving some illustrations or some applications of the use of nets, I want to mention some reference that I used in this part. It is a book of Kelly. It's an old book, but it's still useful. General topology. Another nice book of Grant called The Taste of Topology. There is a book where the net is used extensively. So in a book of Nigelson, it's called An Introduction to Banach Space Theory.
This is not seen.
This part.
Yes.
I cannot use it. Which part?
I will show you
Yes, exactly.
after this.
No. After. Okay. Okay. Mobility. Okay. another book for long. It's very famous. So I think it's real analysis or real. Okay. Now I will give some examples. So examples of the use of convergence nets. I think that in the first one, the proof with nets is easier than other proofs. Just one application in this equivalent. So if we take K, a compact space, then we have equivalence between, say, of K, the space of real continuous function on K is separable if only if K is not resolved. In this application, we don't use net. In fact, we use the Stone-Weierstrass theorem. But I will prove this part with nets. So I assume that say of K is separable. Then we can take, we have a countable dense subset. We can also take a countable dense subset of the unit wall. So let Fn be a dense countable dense subset of the wall unit wall. Now we will construct a distance that gives the topology. We define a distance, so we define a distance d by the distance between x and y is the sum of this series so it is easy to say that it's a distance. Just we explain why the axiom of separation. So if the distance is equal to 0, this implies that this is 0. So for every n, Fn of x equal to Fn of y, and this implies that f of x equal to f of y for every f, say of k. Now, this implies that x is equal to y using Urizo and lemma. For these, to check that it's a distance to other condition, easy to check. We will show. So we have a metric. Now we will prove that this metric gives the exact thing, initial topology. Observe that if X alpha converge to X, then in the initial topology, then f of X alpha converge to f of X for every f in C of K, in particular for Fn. And this implies that the limit of this serial we want to show that the distance between X alpha and X converge to 0. But just we need to permute here the limit and the sum. So we need to explain why we have this. So this is right because this is a version of dominated convergence theorem. Because it is 2 minus n. This is less or equal than 2, so we can dominate independently on alpha by convergent areas, so we can permute limit and the sum. In fact, we can prove a more general result about this. I will mention later when I speak about all the convergence. So this means that this means that the map identity from K with the initial topology to K with a metric space with a metric is continuous. We can show that here we have a choice to show that this is a compact. So using Tikhonov theorem, or you show that if X alpha converge to X, then X alpha converge with the initial topology. And to prove this, it is clear that if X alpha converge to X with the distance, then Fn of X alpha converge to Fn of X for every n. Now this allows to show that for every f, because every f is a limit of sequence from this set uniform limit. And then if you have uniform limit, I recall here that if Jn, Jk converge to J in C of k, and X alpha converge to X in K, then here we can do it elementary. So we can choose Jk in the set Fn such that Jk converge to F. And now I want to show that f of x alpha minus f of x converge to 0. This is f of x alpha minus jk of x alpha plus jk of x alpha minus jk of x plus jk of x minus f of x. And this less or equals 1 is quantity, and this quantity are less or equal than f minus jk plus jk of x alpha minus jk of x. Now, if we can make this, we can choose k such that this is less or equal than epsilon if we fix some epsilon, and we can choose alpha 0 such that for this k, this is less or equal than epsilon. And now this will imply that x alpha converge to x, because there is an equivalence between x alpha converge to x and f of x alpha converge to f of x in say of k. We use here the fact that in say of k, in k, x alpha converge to x is equivalent to f of x alpha converge to f of x for every f. Okay. Another example, if we take X is a Banach space and X double star, it's X by dual. Here the proof of nets is not really the easiest one, but it can help to treat some special case. If we take X double star in X star, so of course here we have a canonical map from X to X double star to X J of X. And if we take here an element in the dual, we want to know when this element comes from X. And the answer is that this element is weak star continuous. So the equivalence between this fact x, there exists x in x such that x w star is equal to j of x, if only if is weak star continuous. Weak star continuous means that if x alpha converges to 0, x star implies that and this means that I recall that x alpha star converges x star to 0 means that x alpha star of x converges to 0 or of y converges to 0 for every y in x. So I will show this. I will give a proof with nets to this fact using Goldstein theorem and give a special case when x is separable. So we can characterize here it's sequentially weak star continuous. And this trick is used, for example, to give a short proof of Green's median theorem. Also, we can characterize element or joint element. So this is A and B. If we take an operator S from Y star to X star, we want to know when S is equal to some T star. And the answer is related to weak star continuity. So the statement is the following. So S is the adjoint of some operator for some T in L of X1, if only if S is weak star to weak star continuous. So let me give the proof of A. So, of course, I will prove one implication. So assume that X double star is weak star continuous. And I want to show that X star belongs to J of X. So if X double star does not belong to J of X, this is closed in X double star. So by Banach theorem, there exists theta in X in the dual of X double star such that theta of X double star equal to 1 and theta of Gx equals 0 for every X in X. I can assume that x double star in the whole theta. I will take just positive, and we assume that theta is as normal. So by Goldstein theorem, there exists x alpha star in the unit ball of x star such that x alpha star converges to theta weak star. So Goldstein theorem said that the unit ball in X in a Banach space is weak star dense in the unit ball of the Baidu. Okay. So we have what does mean this? So in particular we have x double star of x alpha star converge to theta of is some positive element. But also x alpha star of for every x in X, this is equal to gx of and like this. And this converges to theta of gx equals 0. So this means that x alpha star converge weak star to 0. So here we apply this to x double star and to gx. And this gives as x double star is weak star continues, we get x double star of x alpha star converge to 0. But this, we get a contradiction. So we can identify elements in Baidu that are in X by weak star continuity. For B, I think the proof for B is easier. Then if we take an operator from Y star to X star, and also here there is one application that need to be proved. So we assume that S in this space is weak star to weak star continuous. And what is our purpose? We want to show that S equal to T star. So we want to define T. So fix x in x. If we consider this map, so we have to show that, what does mean this? This means that what we want to show that S star of Y star X equal to Y star of TX. This relation. So for every X, we can define a map. The map from Y star to R to Y star S Y star of X. This is clearly linear, and we can check that it is weak star continuous. In fact, if Y star alpha converge weakly to 0, then by assumption S Y star alpha converge weak star to 0, and then S Y star alpha of X converge to 0. So this is given by our assumption. So there exists an element. So this isn't in the bidual of Y, but it comes from an element of Y. And this element depends on X. So we can, there exists Y that depends on X, such that Sy star of X is equal to Y star of Tx. This is Gx Tx, or Gy Tx of X. Now, T is linear. It's an easy fact. And T is bounded also. Why? Linear, it's easy. And bounded, we have, we need to show that T is bounded. This means that the image of the unit ball is bounded. But observe that Y star of T of Bx is exactly as Y star of Bx. And this is bounded because Sy star is continuous for every Y star in the dual of Y. So this means that this set is weakly bounded. But we have an equivalence between weakly bounded and bounded due to the uniform bounded class. So T of the X is weakly bounded. Then bounded by the uniform bounded task. Okay. Now I will give a last application, which is a proof of lemma 151 in Albiac Elson book. This lemma is used to construct some basic sequence satisfying some conditions. And I think why I choose this lemma, because I think that the proof with nets is very neat and somehow natural. So the lemma said the statement, let X be a Banach space and S is a subset of the dual of X. Satisfying this condition, so 0 belongs to the weak star closure, but not to the norm closure. And we take E is a subset of X star is a finite dimensional subspace. It's a technical lemma, and we have an epsilon positive. This is all assumption. Then
sorry, is it 0 belongs to the weak star closure and also to the
it does not belong to the closure. Thank you. Under all these assumptions, there exists some X star in S. Let's find this condition. E star plus lambda X star is more or equal than 1 minus epsilon, the norm of E star, for every E star in E, and for every lambda in R. For the proof, we will argue again by contradiction and assume that this is not possible. So for every choice of E star and lambda, for every choice of, it is possible here to, if E star is 0, then it is trivial. And for E star non-zero, we can only prove this for E star with norm 1. So it is sufficient it is enough to show that for all E star in the sphere. Because we have this lambda, so we can divide by lambda, divide by the norm, and here it doesn't depend on lambda. Okay, so we assume by contradiction that it's false. So for every E star in the sphere, there exists some lambda such that we have this. And for every X star in S, we can find an element in the sphere and lambda such that this inequality is not true. So I will take a net X alpha in S such that X alpha star converge weak star to 0. This is our assumption. And also, as 0 is not in the closure of S, we can find some delta positive. There exists some delta such that the norm of X alpha star is more or equal than delta for every alpha. Okay, so for every alpha, we assume that X alpha star is not a candidate here. So this leaves two nets in the sphere of E. This condition, this one. So by contradiction, there exists E alpha star and lambda alpha such that E alpha star plus lambda X alpha star is more or equal than, is less or equal than 1 minus epsilon, is less tricky. This is because we work in the sphere. Okay, now as E has finite dimension, by taking a subnet, we can assume that E alpha star converge to some E. In E, which has finite dimension, weak star convergence and convergence are the same. And the limit is this sphere is closed. But for lambda alpha, we need lambda alpha to be bounded. But observe that I will write that also lambda alpha converges to lambda. I explain here that lambda alpha is bounded because we have lambda alpha X alpha star is less or equal than E alpha star plus lambda alpha X alpha star minus 1 plus 1. Use the triangle inequality. And this is bound. And this gives that lambda alpha is less or equal than 1 by X alpha star. Now, the last step to get a contradiction. We choose X, let X such that we can choose X in the ball such that E star of X, the norm of E star is 1. So we can choose X such that is more or equal than 1 minus epsilon by 2. So we come here. We get alpha star of X plus lambda alpha X alpha star of X less or equal than 1 minus epsilon. And when we take the limit over alpha, we get 1 minus epsilon 2 less or equal than. This is a contradiction. Okay. Yes. Break. Yes. Okay. Take a break. 10-minute break. Okay, just a few words about the lemma I presented, why I presented this lemma. It seems to be too technical. So this lemma is used to construct some basic sequence satisfying some condition. And basic sequence are used in the book of Carlton I mentioned to provide a proof with basic sequence to a very famous theorem. Just I mentioned the theorem of Eberlein-Smiljan, saying that if A is a subset of X star, when X is a Banach space, the following are equivalent. A is weakly compact. Weakly compact means that every net has a convergent subnet. If only if A is sequentially compact, and this means that every sequence has a convergent subsequence. If only if A is countably compact. And this means that every sequence has a conversion subnet in A. So here, net, subnet, sequence, subsequence, and here every sequence has a conversion subnet. And we have a statement for relatively the same. So for relatively, the limit does not necessarily belong to A. And this is a very useful theorem. So there is many proofs of it. In the book of Carlton and Albiac, there is a proof using Schroeder basis. And the authors claim that this is a easy or short proof, but I found that the proof of Whitney is somehow easier because you need a lot of knowledge about Schroeder basis to do the proof. There is also a proof by Grothendieck, but in the proof of Whitney, we show that if an element belongs to the closure, in fact, it is a limit of net, but we can find the sequence. So it's called angelic space. So in Grothendieck, there is a nice proof, but something missing in the state. So here I mentioned that for weak topology, A need not measurable. So this is a case when there are several cases when compactness can be characterized by sequences, although the topology is not measurable. Okay, there is another missing point, the last, before moving to another topic, which is vector lattices. Last missing point. I want to mention because the proof of this is very natural and easy, and there is the same idea is used to prove something which is which is new and does not remarked for many years concerning all the convergence. Yesterday, I used this property that XA is a cluster point of X alpha if only if for every neighborhood of A, X alpha is frequently in V. And the cluster point is defined via subnet. So to prove this, assume that A is a cluster point. So assume that Y beta converge to A for some subnet Y beta of X alpha. Then if we fix some for alpha 0 in A, there exists. We know that Y beta is of the form. There exists some cofinal map. We know that Y beta is equal to X phi of alpha or some phi from V to A cofinal. Now for every alpha 0 here, there exists beta 0 such that beta more or equal than beta 0 implies phi of beta is more or equal than alpha 0. Also, there is beta 1 such that beta more or equal than beta 1 implies Y beta is in V if let us fix V in neighborhood of A. So we can choose let beta in B such that beta is more or equal than beta 0 and beta 1. Then phi of beta is more or equal than alpha 0, and X phi of beta equal Y beta is in V. This is one application. It's the other that I want to notice. Now assume that A is we know the assumption that for every V, X alpha is frequently in V. And we want to construct a subnet that converges to A. So for every V, and for every alpha, there is a beta that I called phi of V alpha, because it depends on V and alpha, such that X beta belongs to V. And now it is easy to see that the map V alpha is beta is cofinal, and the net x phi of b alpha converge to A. Okay. I will use the same idea to give a proof of something that is not known for a long time and make a connection between two kinds of order convergence. So now I want to say some words about nets in vector lattices. So I start by giving some definitions very briefly. What's a vector lattice? So a vector lattice is a vector space which is ordered, and we assume that the order and the algebraic operation are compatible in the sense that if x is more or equal than y, this implies that x plus z more or equal than y plus z. And this implies also that lambda x is more or equal than lambda y for scalar or positive scalar. And we assume also that it is a lattice. It's a lattice. This means that for every x and y, the supremum exists, and usually denoted by like this, and the infimum also. So the supremum of any finite subset exists. And if you want to give examples, so the font-wise order, and most of function spaces are vector lattices. So say of k with another order, so font-wise. So in measurable spaces, LP spaces, L0, here we deal with the classes. And we are used to work with order in these spaces. We are used also to define the positive part and the negative part of functions, deal with increasing function, integration, measure theory. So similar here, we defined the positive part and the negative part and the absolute value, etc. Okay, so I want to mention some substructure. We have this structure is vector lattice. Substructure is called vector sublattice. With usual definition, it is closed under algebraic and lattice operations. We have also ideals or solid subsets. So A is solid if we have the following property: if X belongs to A and Y is less or equal than the absolute value of X, then Y belongs to A. Ideals are solid vector sublattice. I will use abbreviation now, be faster. And there is an important notion called bands. A band is an ideal plus an additional thing that it is closed under taking infinite supremum. So if X alpha, if A, so it's closed under taking supremum. This means that the supremum exists. So the precise definition, if A is contained in our let's say Y. So Y is an ideal, and we assume that we have a subset in Y such that the supremum of Y exists, then the supremum belongs to Y. Okay. We use this notation that if we have a net, we come back to nets. If we take a net in a vector lattice X, we write that X alpha is increasing if X alpha less or equal than X beta whenever alpha less or equal than beta. And for decreasing nets, it's similar. And we write X alpha increasing to X. This means that X alpha is increasing and X is the supremum. Also, this notation is used for sequences and increasing function, etc. I want to mention some specific sublattice. It's in literature we can use the term sublattice instead of vector sublattice, because in general people are interested in vector space, which is a sublattice. It's very common to use the term sublattice to mean vector sublattice. So I want to give this definition: regular sublattice. So I take a sublattice in a vector lattice. I will say that Y is regular if we have the form. If Y alpha, I can give with set. I will give some equivalent properties. If a set is contained in Y and alpha, I will say M is the supremum of A on I in Y, then also M is the supremum of A in X. This is equivalent or the same when we work with infinite. And this is equivalent to work with nets decreasing to 0. etc. Another definition, another notion, which was order dense. So Y is a vector sublattice again, is order dense if for every x in x plus for every x in x with x is strictly positive, so x is positive and not zero, there exists y in y, that's fine, this condition. And y is majorizing if instead of have an element below x, you have an element above x. So it's the same, there exists y such that okay. A lot of definition, but they are needed to make some work. We want to go back to net and convergence. So I will speak about order convergence now. I can give an example before giving the definition. So in L1, for example, Fn converge to F in order is equivalent to Fn satisfies the condition, the conditions of the assumption of dominated convergence theorem. So the convergence, the dominated convergence theorem can be stated as follows: if Fn converge to F in order, then Fn converge to F in L1 in order. Okay. Later I will give the translation of convergence in order in C of K space. So the definition, I work always in a vector lattice. I will say that X alpha converges in order to X if there exists. So the convergence in norm for every epsilon, there exists delta. So it's similar definition here. There exists net y beta indexed by another set such that y beta is decreasing to 0, and for every beta 0 in B, there exists alpha 0 in A such that alpha more or equal than alpha 0 implies x alpha minus x, the absolute value, is less or equal than y beta. You can think for every epsilon there exists a delta.
Beta C.
Beta 0. I can mention some properties that can be proved easily, that order limits are unique. And order convergence behaves very well with algebraic and lattice operation. This means that x alpha converges to x, then x alpha minus x converges to 0, x equivalent to the absolute value and if you have x alpha converge to x and y alpha converge to y, then x alpha plus lambda y alpha converge to x plus lambda y. All convergences are in order. And the supremum converge to the supremum, the infimum. Yeah.
Does this hold if we change the index set of one or the other or the second net? So we have x alpha and y beta.
Yeah, if x alpha converge to x and y beta converge to y, yes, we have x alpha plus y beta and fixed y is. Okay,
Same with subs.
the subs and the infimum also. So it behaves very well with operations, algebraic and lattice operation. Also, we said that x alpha converges to x implies that x alpha has order as an order bounded tail. This means that the net itself could be not ordered by, but there exists some alpha 0 and some 1 such that x alpha is less or equal than y for every alpha more or equal than alpha 0. Okay, I want to mention another definition of order complete vector lattice. So X is a vector lattice, is order complete if for every set A having an upper bound supreme of A exists. We can state an equivalent definition with lower bound. And it will be related to order convergence. So order complete means completeness in normal space means that every Cauchy sequence is convergent. So we will prove a result like this. So the space is order complete if only if every order Cauchy is order convergent. It's also called dedicant complete. There is another equivalent terminology. For example of spaces that are order complete, dimension, finite dimension, RM, L infinity, LP, C0. The space of continuous function is order complete for strange property. So it's order complete. Take A for that. If only if A is extremely disconnected or Stonian. Stonian means it's also called extremely disconnected. This means that if you take V open, then its closure is also open. We can speak about sigma order completeness when we deal with sequences. Lim-sup and lim-inf. If we deal with bounded sequences, bounded nets, and work in an order complete vector lattice, so if X is order complete and X alpha is order bounded or under bounded after some time, then we can introduce we can define the lim-sup of X alpha as follows. It's amphonon of supranon. Like for sequences in R. And this is defined because it's order bounded. And with inf, take the inf before and the super. In fact, the super is a limit because it's increasing. You can observe that for increasing sequence, the limit is the super, like for the real space. So we have a theorem. Under this condition, X alpha converges to X if only if the lim-sup of X alpha equal to the lim-sup of the lim-alpha of X alpha equal to X. How much time is it?
20 minutes.
Okay. For the proof, I need to do some proofs. Before giving the proof, I want to make some observation. I don't know if I need the observation now. If I need it in the proof, I will prove it later. Okay. So assume that x alpha converges to x. So if x alpha converges to x, so there exists a net y beta such that y beta is increasing to 0 and satisfying the definition. The definition says that if you fix beta or beta in B, there exists some alpha zeros that start x alpha minus x is between y beta and minus y beta, or alpha more or equal than alpha 0, beta 0, or x alpha is between so if you look at this part, we see that this is an upper bound. This means that the suprabound is less or equal than y beta 0 plus x. But this is the lim sup is the infimum of all these quantities. I will take big L, the lim sup. So L, what we get here, L is less or equal than y beta 0 plus x. Or if you want, L minus x. And this happens for every beta 0 fixed in the V. So this is a lower bound of this net, but we know that this net is decreasing to 0, but it's not from 0. So L minus x is less or equal than 0, or L is less or equal than x. So in a similar way, we show that. So we have the lim sup less or equal than x. And if we look at this, we can show in the same manner that this is less or equal than lim up. But the lim sup is bigger than the lim up, so we get equality. Because as in the usual case, the lim infimum is less or equal than the lim sup. Okay, for the other application, assume that the lim sup of x, we assume that this equality holds, and we want to show that x is the limit of x alpha. So observe that X alpha is less or equal than the supremum of X beta or beta more or equal than alpha. And if write this Y alpha X alpha Z alpha. But this net is decreasing to X. So X is also between Y alpha and Z alpha. So observe that Z alpha is decreasing to X and this is increasing to X. And then we get this equality, X alpha minus X is less or equal than Z alpha minus Y alpha, which decreasing to 0. In the definition, I make this observation. In the definition of order convergence, we say that X alpha converges to X if there exists some Y beta, etc. And this is equivalent to the fact that there exist two nets, Y beta decreasing to, I will say, B beta decreasing to X and A gamma increasing to X, that X alpha is between, for every beta and gamma, A gamma B beta. The definition gives that X alpha, this is satisfied eventually for alpha more or equal than alpha 0. This is given by, if we have this definition, then we get that X alpha is less or equal than X plus Y beta more or equal than X1 minus Y beta. And here, the same, we have the same index. But we can manage here to get the same index by indexing by the pair beta alpha. A useful remark here that if you work in an order complete space, the net Y beta given in the definition can be indexed by the same index set. So if X is order complete, observe here that we have the same index. Then we can choose B equal to E in the definition.
No, no. No, right there.
Okay. In the definition of order convergence. In fact, in the literature, there is two definitions. This definition given in the beginning, and another definition using the same index. I will write X alpha converge to X O1 if there exists Y alpha decreasing to 0 such that X alpha minus X is less or equal than Y alpha eventually. And these two definitions are not equivalent. They are equivalent if we work in an order complete vector lattice. In fact, we have this result. Before the result, I want to give a definition. So if X is order complete, okay, we can choose the same index set and we can use lim sup and lim inf. But if X is not, what we can do, we can work in the completion. So there is a notion called order completion. So if we have an Archimedean vector lattice, I will recall the definition of Archimedean. So let X be an Archimedean vector lattice. Most of vector lattice we used Archimedean. Then there exists an order complete, vector lattice denoted by X delta. Vector lattice X delta, such that X, in fact, we can embed X in X delta and then we identify X with its image. So I can assume that X is an order dense. X is order dense and majorizing. An order dense and majorizing vector sublattice, I will say, of X delta. And if there is another, then both are isomorphic. So as usual, compression is unique up to isomorphism. So this is called the order completion of X. Is many construction of order completion, technical. I will give a theorem here. In fact, the theorem is general. If X is a vector sublattice of another space, and X is majorizing and order dense, then order convergence in X is equivalent to order convergence in subspace. I will give the statement in for the special case, which is more important. So let X be a vector lattice. every time we can work with net convergence to 0 because it can make the difference. So, and x alpha denoting x, then we have equivalence between x alpha converge to x if only if in x to 0, if only if x alpha converge to 0 in x delta. And this one of reasons that makes our definition, the first definition given, is better than the other. For this definition, first given in the beginning, we have this result. And it is trivial that if x alpha converge to x O1, then it converges to x with this general definition. And the converse is false. I will give an example. So I will do the proof later. Just I want to mention some remark that x alpha converge to x in order implies O1 implies x alpha converge to x in order. Here we use the same and x set. The converse is false. I will give you an example. And the converse is true. Using this theorem, converse is true if x is order complete. So these three results are all known before some years. So the connection between these two kinds of conversions, this is more general. They are equivalent if the space is order complete, and there is a trivial implication. And the other implication is wrong. So now I will give an example showing that this implication is wrong, and then give a positive result. I discovered several years ago, but I didn't publish. And it was published by another people. But the matter here is, the point here that, yes, 1 minute. So I don't have time to prove anything, just I will give a new connection between this kind of convergence. So if x alpha converge to x in general definition, then there exists a subnet y beta such that y beta converge to x O1. And I don't know if I give an example, just or maybe I stop here. Next time I will give an example and prove these results. Okay.
Okay, thank you.